Yeah, so I know a lot of my talk is how old. And the idea is that, right, when we observe gravitational waves from the black hole of that we're observing the last like this. But if you rewind that back in time, those two black holes started off further apart and they've been evolving through the gravitational radiation. So then the question is, okay, how far back are we actually, like when were those two black holes, or how far in time? And that depends on their initial distance from each other. That's the first thing I'll derive is the fluorescence. And so the system that we have here is we have your x1, x2, x3 coordinate system. And you have some binary that lives in the x1, x2 plane, and this coordinate system is in the center of mass of your binary. So you have some black hole mass M1, other black hole mass M2. This is the center of mass. This guy is at R1, at R2. This angle here is 5. And this binary is in the x1, x2 plane, and we are observing up here at the x3 plane. So that's like this. Okay, so this is the binary system, and I'll just define some things that we have. So the orbital separation is the sum of R1 and R2, orbital separation, of the total mass, and of those two masses. Another helpful mass parameter is the reduced mass. Like if you prefer to think in terms of mass ratio Q and 2 over F1, that's Q. And then because we're in center of mass coordinates, we have R1 is A is over M, and R2 is A over M. And then the gravitational wave luminosity in this linearized gravity where you have some small perturbation over flat space-time. The first order term of that is the quadrupole, the mass quadrupole. And I won't derive this, but you have this formula, famous quadrupole formula for the change in energy divided by time is given by G over C. So that's it. And then I here is the quadrupole. The third time derivative of that mass quadrupole enters in here, and I'll just write a little line through here which denotes that this is the trace list for so subtracting the trace from the mass quadrupole. Oh, sorry. Yeah, so this is the gravity luminosity, and so what I'll do in the next little bit is you can think of that energy that's being radiated gravitational waves is coming from the orbital energy because the orbit is shrinking as the gravitational waves are radiating away. So you can solve for this gravitational wave energy loss, set that equal to the orbital energy loss, and then get the time evolution as a function of the orbital separation of position A. And so to do this, we have to go through some math. So the quadrupole here, the quadrupole tensor is just defined as the density field integrated over like the body that you're talking about. In this case, we just have these 2 point masses, so the density field is just a delta function at the location of M1 and M2, and so this just reduces to a sum. To this sum, and so we can just plug in what these are to solve for all of the components of this tensor in terms of ij. So here, R1 in terms of phi is, so that's R1 vector in this coordinate system is R1 cosine phi, R1 phi. And then in that there's 2 planes, so there's no 3 components. And then 2 is negative by 2. 2. And so we can plug in for all the different components of I, which again, we're not going to plug into this formula to solve for the gravitational wave luminosity. And so the non-zero components, we need 3 components are going to go to 0. So the non-zero components are I11, I22, and then I12, which is equal to I21. So there's some trigonometry here that you can solve for I11, which is now M1 R1 squared squared phi. So taking up these R1 terms, and 2 squared phi, which we can rewrite using this in terms of A and the reduced mass. So you can get this to be U A squared phi. And now using trig identities will be useful when we add everything together. And squared is half. Phi. Okay, so that's the 1,1 component. Now we can write the 2,2 component, which is similar, but now we're picking up R1, 2, and R2, 2. So we're going to get sines instead of cosines. And that is just going to be 1 R1 squared, 9 squared, phi plus 5. And so this A squared 1. Phi. Okay, and now the last non-zero term of this tensor is 2 plus 2, 1 And that is, now we're going to have M1 R1 cos phi times R1 sine phi, and then similarly here, cosine and sine. And so if you plug that all in, it's mu a squared or sine phi cos phi. Okay, great. So now we have all the non-zero elements of this tensor. But in order to solve for the gravitational wave luminosity, we need the third time derivative of this tensor. And so remember, these are all functions of time because phi, oh, I didn't actually write this down. But here phi is a function of time because it's inspired. And so this is the angular frequency omega, and this t is time. And so we can, all of these phi's here are omega t's. So if you take one time derivative, you get an omega out front. You take 3 time derivatives, you get omega cubed. And then from this, here we have a cosine term, so it'll turn into sine, cosine, and then sine with a negative sign. Here we have cosine, sine. You'll have first time derivative is sine, then cosine, then sine, canceling out this negative sign, and you'll have a cosine. And so just writing that out, this is going to be 4 mu a squared omega cubed, to not be in space, but negative 9 to 0 cosine, and then all the third row and third column elements are 0. We have nothing in the x3 plane. Okay, so that is this third derivative of the mass quadrupole. You can see that it's already traceless because if I sum the trace, it's 0. So that's good. Now we can just plug it into this equation. So we're going to be adding all of these terms, the square of them. So
The interest is, there's no difference, it's just pi and bar.
yes, yeah. So here at least when you take the time derivatives, it's already traceless. So yeah, we can just treat this as I bar. And so then, yeah, we basically want to write sum over all the ij's. And take the time average of this. That's what these brackets mean. But when we do this, you can see the this is sine squared plus cosine squared, which is 1, plus cosine squared plus sine squared, which is another 1. So we just have 2 here, and there's no more time dependence. So also this average over time term becomes irrelevant. And so this part is basically just equal to squaring everything. A to the 4th, we'll end up with a 6. 2, and just adding all those terms together. And if we plug this into there and multiply that by g over 5, c to the 5th, we get that the gravitational wave luminosity is 32 over 5 E over e to the fifth mu squared e to the fourth omega to the sixth. Okay, so this is the thing that we're going to set equal to the orbital energy loss to get the time evolution. Okay. Does anyone have any questions before I raise them?
So I have a question. So here you assume that omega is constant, but that essentially should be changed depending on how much gravity wave you're assuming. So you're assuming that the amount of energy emitted from the gravity wave is very small.
Yeah, so omega is also a function of time, but we're thinking this is really yeah, in this limit where it's kind of like over one orbit. So in that, yes, in this limit, we're assuming that omega is not changing much with time over that like single orbit that we're looking at.
Just think it's related to the validity of the constitution.
Yeah, but you can use this to solve for the time evolution of omega and A. So like this is kind of over a single orbit, but then we'll see that this is going to give us a pretty good approximation for the evolution for the whole atomic curvature of the time scale and of the evolution of omega, which is the chirp of the binary. Yeah, so let me just this. Okay, great. So this is the energy that's getting radiated in gravitational waves. And we're going to, so this energy loss is coming from the decay of the orbit. And because this linearized gravity approximation is basically treating the background metric as flat space-time, that's just Newtonian gravity. So we can treat the orbital energy as just the Newtonian orbital energy. Which we took like from Kepler's law. So that in terms of total mass and this reduced mass ratio, sorry, I have trouble writing 9 U's over 2A. And so the time evolution of this in terms of the time evolution of A is A times. Now we're explicitly putting in that A is evolving with time. And we want to set this equal to that. Or to the negative of this. So canceling out. So. There. Okay, yeah, so now we want to solve for A dot as a function of time, and to, so let's just move some terms over. Onto this side, and we can write omega in terms of A just from Kepler's laws. That's omega squared equals over A cubed, and so we plug this into that. Take the cube of this so we can plug it directly into that, and that gives us that A dot is squared A to the minus 3. Okay, so now if we want to know how long this binary takes to merge, that's the coalescence time. We can just integrate out the time. So basically what we're doing is starting from an initial A dot, treating like these black holes as really point particles, so they don't have horizons, ignoring that finite effect, and just taking the evolution from A naught to 0. So I'm assuming that this system evolves from A naught to A40 when the time evolves from 0 time to the coalescence time, tau c. And now if I just do this integral, I'm going to get, this will give me negative A0 over 4 equal to and I can rearrange all of this to give me that the coalescence time tau c as a function of A naught is 5 over 256 c to the 5th over b q mu squared A0 to the 4th. Okay, and this is the famous Peters formula from a paper by Peters in 1964. It shows you that the coalescence time scales with the initial separation to the power of 4, which is pretty extreme. So it takes, like, if you change the initial orbital separation by a little bit, you're suddenly going to take a lot longer to merge by gravitational radiation. And just to plug in some numbers here, you can see how inefficient gravitational waves are at actually shrinking orbit. And see that if I look at 14 gigayears around the age of the universe, then and I'm going to write this u times m squared in terms of the mass ratio cube. It's easier for me. And if you think of a binary with an initial mass of 20 solar masses, then you need an initial separation that's around 0.14 AU in order to merge within 14 gigayears. In the Q equals 1 case, so for an equal mass binary, then this is around 20. So for then you need the initial orbital separation to be around 20 times the solar radius for total for 10 solar mass black hole plus 10 solar mass black hole. To merge within 14 gigayears, they initially have to be separated by only 20 solar radii, which seems absurd because if you have a star that's going to produce a 10 solar mass black hole, it's probably going to expand to 100 solar radii just in its lifetime. And that's why people try so hard to, invoke these common envelope phases, et cetera, so you can rapidly shrink the orbit and end up with two black holes that are really on order of like 10 solar radii apart.
Just a comment, a useful way of remembering this formula, maybe not the coefficient, is that you can express it as light crossing times across the pole and sun times ratio of A to the gravitational radius G of C squared. Whereas the orbital view is the light crossing time across the black hole times A over the A over the gravitational radius. We have some, so it's much larger problem than this moving the about it approximately.
Yeah.
Something about the fact that Q, you have Q in this comment there, so you have a large mass ratio, it's like it speeds up this process. Oh, no, it slows down.
Large, so
This Q is
Q is less than 1. So the slowest is for an equal mass binary, and for a very asymmetric binary, then it's faster.
If Q is less than 1, then it makes the closest line bigger.
Oh, yes, but then sorry. The large,
The fastest
Yeah,
closest
is that-
thing is equal mass.
the largest this thing is when Q equals 1.
If the Q is much less than that. If Q is 1, then that's 4. 1 plus Q squared is.
Yeah.
If Q is much less.
Oh,
than
yes,
that,
yeah,
that's
this is the inverse of the of eta. The mass dimensionless mass ratio.
sorry.
Yeah. No, right. So this is, yes, that makes sense. The time, if Q in the limit of Q goes to 0, which is very asymmetric, then this becomes very large, which makes sense. So the fastest in spiral is for the equal mass case. Yeah, that makes sense. Another thing that is assumed here is a circular binary. If you have eccentricity, or we say quasi-circular, if you have eccentricity, then this equation becomes a lot more complicated. But essentially for the same orbital separation, the eccentric systems will merge larger, will merge faster. Yeah, but okay, does anyone have any questions about this before?
On this interest, they circularize as well from gravitation?
Yes.
So, sorry, I was here, so the gravitation, or the circularization time scale is much faster. And that must be, so must be separate. Angular momentum. Gravitation.
Yes, yeah, so the Peters 1964 is the reference. That deals with general eccentric binaries. But yeah, it's not a simple formula, like there's an integral in there that you have to do numerically.
Is electricity ever big enough correction to the power, the luminosity? Yet you're still in the regime where this quadruple, an average quadruple approximation works. So I would imagine if you get really eccentric, right, then you're just zooming by very zooming quite close. Higher order corrections. This one?
Yeah, so with an eccentric system, it does make a pretty big correction when the two are still pretty far apart, so they don't actually get, like, you're still not ever getting close enough together. So this approximation breaks down. And at that point, you've essentially circularized. So those are the cases we think about.
Essentially given by the emission circular quick. So the matrix is equal to the areas. And so basically, you fully built the list when you pass the list, it's just crashed together.
Yeah, I mean, so it's really hard to get to come up with a scenario so that you still have eccentricity by the time that you're, say, in the LIGO band at 10 Hertz. You basically need to start your, so this can work in a dense cluster where you are essentially starting at a point where you're like already eccentric. So they're just close to a direct capture scenario where you just have a bunch of things flying around. It's really hard to start like further away with eccentricity because gravitational waves will get rid of it. Okay, so then back to the question, how old are LIGO's black holes? This tells us how to go from, if I knew the initial separation, I can solve for the coalescence time using this formula, but I don't, for a given binary, I don't know its initial separation. But the assumption that we make is that there is some distribution of initial separations, and so that can give me the distribution of coalescence times. And so this coalescence time is just the time that starting from two black holes at some initial separation, how they'll take to merge. When we're talking about the evolution of these systems, we usually talk about a delay time, which refers to starting from two stars, how long until they become a gravitational wave merger. But this gravitational wave coalescence time is so long that it's going to dominate any other time scale. Like it's much longer than stellar evolution time scales for massive stars and anything else really that happens before you get to the situation of two black holes. So the delay time is really just driven by this coalescence time. So even though when you start off with your stellar binary, it's not at this orbital separation, otherwise your stars would merge and you would never end up with two black holes in your system. This is still the scaling that we typically assume for A being like the actual orbital separation of your stars. And then what we're interested in is this delay distribution, which is this statistical distribution. So even though this delay time is different from the coalescence time tau c, I'm going to just, it's dominated by tau c, so I'm going to just assume that they're the same thing. And then that gives us that if we want to know what this distribution is in terms of the distribution of orbital separations, we can just do our probability change in variables, where these T's are just probability distribution functions. And I'm just labeling them by the variable that they're defined over. So this is by just probability change of variables. This delay time distribution is given by my orbital separation distribution times this Jacobian. Because tau goes like e to the fourth, then this Jacobian is e to the -3. And then if I want to express this in terms of tau, then a goes like tau to the 1/4. And so then I get that the time delay distribution is proportional to E of k evaluated at tau to the 1/4 times tau to the -3/4. And so we typically assume that the initial orbital separations are distributed according to some power law. So if we did have E of A that scaled with some power law, so beta, then plugging that in here would give us that this P of tau scales as tau to the beta -3 divided by 4. And another typical assumption that we make is that this is actually beta is -1. So we have a flattened log distribution of initial separations. That's what observations kind of give you sometimes. And so in this case where beta is -1, then it's actually quite convenient to remember because P of A goes like e to the -1, and then P of tau would also go like tau to the -1. So a flat in log distribution in initial orbital separations is also a flat in log separation, a flat in log distribution of your delay times.
It's not true for any parallel relationship. There's flat and long one the other. The logs are related.
And
Sorry.
Yeah.
It's an important point. It's just, two things are related by power law. You have a proper distribution that's flat in the log one, it has to be flat in the log the other.
Yeah, right. Yeah, so no matter what power law, if it's not special about before. Yes. So, okay, so this turns out to be pretty close to what people get, like this flattened log distribution in delay time is pretty close to what people get from population synthesis models. The main thing that is going to change this is, again, we made this approximation that this delay time was equal to this coalescence time, where we start off with we're talking about the separation of the two black holes, whereas in general, this is talking about the separation of two stars. So you can get things that are steeper than this. For example, if you have common envelopes that are very common, and so that kind of causes this big jump between this A, which is your stellar separation, and this A naught, which is your black hole separation. Chris and then Reed.
Well, you were starting off by considering essentially a word. I was wondering if, since there's so much discussion of the hand clusters, is there some general sense of whether this is?
Yes, you should read my latest paper.
Sorry.
Yeah, so, no, yeah, that's right. This is talking about primordial binaries, like, or we often call this isolated binary stellar evolutions. From globular clusters, you would get a different distribution, often skewing to much longer delay times because the mergers have to first get ejected from the cluster, and then we still have to put wide orbital separations before they merge. But yes, we do think that these are in our data, isolated stellar evolution. And the main reason for that is we see a preference for spins that are aligned to within 90 degrees of the orbital angular momentum. And really any kind of preference for spins like away from an isotropic spin distribution points to binary stellar evolution as opposed to globular cluster that's just randomly assembling for black holes. That kind of robustly predicts sort of an isotropic spin distribution. We don't see that in our data.
So, okay, I'm a little behind. I actually have to say, on papers that live in Monte Carlo and so on. And I haven't sat down and read in detail. So now on the conditions, obviously the assumption is like you have to pre-body interaction. There's absolutely no reason why this still should be.
Yeah.
But if I had like a tidal interaction with black hole, say star, I guess we have to be acid, super, I guess supergiants will last. The massive stars won't last. So tidal interaction with black hole, super. Then it's not obvious that all the accretions what the orientations.
Do you mean that then that would eventually evolve to become a binary black hole?
Could that not evolve to become a binary black hole with spins already?
Yeah, but that wouldn't really happen in a globular cluster because the interactions are too frequent. So you don't end up keeping a binary between a star and a black hole.
So the point is that add what essentially a different channel for this massive stars and last very much. This is happening for non. So that this alternative channel for binary. When those binaries we get this from. Or they emerge very.
Yeah, I mean, the assumption is that those binaries would get disrupted, and also you end up in a situation where dynamical friction is causing the black holes to sink to the center, and so really all the interactions are black holes involved with other black holes in a globular cluster type system. Then there are young star clusters or clusters that are less dense than globular clusters where you do have this binary evolution interactions that are more important, and that's just really hard to simulate right now. Is to have proper binary evolution plus dynamics in systems where that's important. So this is also the problem of simulating triples.
Yeah. I'm just trying to think. Sorry, what?
Yeah, I was just gonna ask, very said it, but when you talk about the delay time, it's the delay time between what's the events? Like merger, like actual coalescence, or what's the start time?
Yeah, so yeah, sorry, that's what I was trying to say. So here with the coalescence time, it's when you start off with two black holes, how long it takes to merge. When I talk about delay time, I'm talking about from the binary stars, and again, assuming that it's a binary star is the initial conditions. So you start off with two binary stars, then they evolve, and then they become two black holes, and that's where this takes over. So there is extra time in the delay time distribution, and so when I'm talking about A here, that's the initial separation of the stars. That's what we can measure from surveys. And get an example of binary stars, and we can kind of measure the initial orbital separation. But the assumption is that this delay time is very, very close to the coalescence time, because everything that happens before that happens much, much faster than just the coalescence.
So observationally, the handle on the delay time would be a different redshift distribution for the coalescence versus the star formation distribution. Because you're not gonna be able to find a galaxy, should this happen, so you can't tell its
Right.
particular star formation history is.
Yeah, unless it's a binary neutron star. But yes, yeah, so what we measure is, let's see, I have like 5 minutes left. What we measure are the redshift at merger. And if we have some idea of what the delay time distribution should be, we can infer what the redshift at formation is statistically. So for each one, we don't know what the delay time is, but if we have some idea statistically what the delay time distribution is, then for our statistical sample of merger redshifts, we can infer what the formation redshifts are. And so what I wanted to do next is talk about what's the longest delay time that we probably have seen. So yeah, so let's say we have and mergers, and let's say they're all roughly at redshift of 0 right now. Then we can talk about the maximum delay time in this sample. And you might want to know, okay, what is this maximum delay time example, assuming that these delay times are drawn from this flattened log distribution. Right, so each one of these G's are drawn from that. Then the distribution of the sample maxima is given by, well, basically we're going to talk about the cumulative distribution function of this variable x. And this is just a probability that each one of these t's is smaller than x, because x is the maximum. So that's just the probability that all of these t's are smaller than x. The probability that t is smaller than just x is just the cumulative distribution function of tau. So my CEF of the sample maximum is just the CEF of tau to the power n. And so you can see very quickly that the sample maximum is just going to approach the maximum delay time ever, which, assuming these mergers are all at redshift 0, that the maximum delay time possible is just the age of the universe, or really the age of the first stars that formed. And so this is and assuming this flat and log distribution between some minimum time delay and some maximum time delay. to the power n. So as n becomes larger and larger, then x is just going to approach this maximum delay time. And we can plug in some numbers here. So let's say we've seen 70 events. So n is 70. And this is our cumulative distribution function of this sample maximum. And I want to say at 90% credibility, x is above some number. That means that I'm going to be setting this cumulative distribution function to 10% to 0.1. So I can say n equals 70 and set this equal to 0.1. That's going to give me that x is equal to the maximum time delay to the power 0.97 times the minimum time delay to the power 0.03. And so if we assume that this is the age of the universe, the maximum delay possible is just the age of the universe, and this minimum delay is 100 million years, that'll give us that x is around 11.8 billion years. And so at 90% credibility, we've already seen a black hole merger in our data that those black holes were born almost 12 billion years ago, which is pretty cool. And basically out of time, so I can just stop here and ask if there are any questions.
Does that last statement depend all upon the distribution of star formation over the last 12 years? Like, suppose you had a strong, it wasn't in the math, but I'm just wondering, what if you had effectively no stars forming over the 10 years, you know, then
Yeah,
then that statement just said it can't possibly be right. So what's the assumption? Because
so it's what's this maximum? Yes, and it's assuming that the delay times are basically independent of the merger redshift. So that's another thing that this is kind of assuming redshift is 0, but this maximum delay time is basically the age of, or the look back time corresponding to the first stars.
so you just did starts.
Yeah. Any other questions?
Then I can speak again.